Alright, how's everyone doing? Do you have a different Ubuntu download? The one you did never get finished. So you can find like 18.04. That should be safe to use. Actually, let's try this. Go ahead and look for Xubuntu download. 64-bit systems. And 18 might be a little smaller. Yeah, go down to 18.04 long-term support, 64-bit systems. That's a torrent download. I don't have torrent. Alright, so Xubuntu download 18.04, go to United States, and just pop on one of these ISOs. It's 1.5 gig, so you should be fine for your network speed. Yeah, 20 is the current long term, but we're trying to go with as small, non-obsolete a version as possible. Because we're talking modem speeds, maybe. So yeah, give that a shot. I did upgrade to 20 on a virtual system, and it looks like it's fine. So I'll upgrade my main system at some point. But yeah, they are. I don't know. Let's see what the difference in size is. So United States. So yeah, 1.6 versus 1.5, not a big deal. All right, so questions, issues. Nice. Yeah, definitely good idea to stay with the latest version. I like to stay with the long-term supports, so I don't have to upgrade too often. And 20 is good for at least a few years. Awesome. Yeah, like I say, I'm doing 20 on a virtual setup, and it looks fine. It's just, you know, little things that need to be redone whenever I upgrade, so. Alright, everybody good with PA5 so far? So we're going to do Open Lab tomorrow. If you're having issues, come by and let's work on it in there, and hopefully you can finish PA5 soon, rather than, you know, waiting until next week. So Open Lab tomorrow, no new lectures. Alright, so let's talk about synchronizing threads. So we were playing with some code yesterday, and we were incrementing a value in shared memory and seeing that we were getting into some quandaries. So let's go into here. I don't know if this was the version I wanted or not. Okay, this looks good. All right, so I think this was where we left things yesterday. So we have these methods in two threads, and when we run it, we sometimes end up with a final tally. Oh yeah, let me share my screen. Let's see. There we go. And while I'm here, how can you possibly get updates more often than Windows? I thought that was like the clock that kept the universe rolling was Windows updates. Alright, hold on, rearranging things here. Alright, so we've got this code and you know, you run it and it should add up to 20,000 because each thread is incrementing inside a loop 10,000 times. We got 2 threads, pretty simple math. But you know, as we saw, sometimes that happens, sometimes it doesn't. This is probably what we would expect, right? The first thread would count up 10,000, the second thread to 20, but it doesn't always happen. And so we looked at that in terms of read, modify, write operations, and the idea that you know, if these operations are not atomic, then you get into issues where, you know, you're undoing what some other thread had done. So we talked about how to try to fix that by using a flag to say, you know, I've got exclusive access, but the flag itself is subject to this kind of resource contention. So the way in Java we can fix this is to just use a keyword. So we can take this increment operation and we can say, let's synchronize this. So we can say synchronized and then put one or more comments inside a block, and everything inside here can be controlled to make sure that only one thread is executing this set of statements at a time. Now, to do this, we need a flag. We need something we hold up in the air and wave and say, hey, I've got exclusive access. And then when we want to come into this block, if we can't find that flag because somebody else has it, we have to wait. And we will sit here and wait and wait and wait until whoever has that flag releases it, and then we or somebody else who's trying to use it will pick it up, wave it and say, I've got exclusive access, and then their synchronized block will continue. So we have to put a flag in here. So synchronize is not a method, it's a keyword. It's like try catch. It's saying that this code between here and here is only allowed to run if you can get access to this lock, this flag. And we have to specify a flag in here. So it looks like a function call, but it's not. It's really it's controlling the execution of this piece of a thread. So what do we use for an object? We can use any object that's shared among all the threads that we want to synchronize. We happen to have an object already which is shared by all the threads. That's the parent. So we can go ahead and just synchronize on parent. But really any object would work. And if you had different sections of threads that wanted to synchronize with different groups of other threads, we could have a different lock for each one. But since both threads are constructed with the same object, which is the Go object, we can use that for our synchronization, and that should work fine. And if we do that, we will get this rock solid behavior where, you know, the first thread can finish whenever, but the second thread will finish and the count will be 20,000. And our main program is, you know, constructing a Go object, and as soon as that constructor returns, it says exiting, and it prints out the tally. And the Go constructor, you know, creates these threads and starts them, so that returns as soon as the threads begin. So when the main program exits, the tally could be anything. It's usually pretty low. It could be 10,000. It could be 20,000. If the main program doesn't exit until the threads have exited, because that's just how the timing worked out. But in general, you know, main exits pretty early, and then in this case the final tally is 20,000. So that's one way to synchronize code, is to use a synchronized block. And you've got to be really, really tactical with this. Do not put your entire program inside synchronized. Synchronizing defeats threading, right? When I put this in here and I say this is synchronized, it means that only one thread can execute this statement at a time. And if I were to do something like this, right, put that whole for loop inside a synchronized block, well, that wasn't really what I was expecting. I'll make it more dramatic. And I'll put that exit message inside the synchronized block, right? We no longer have, you know, two threads running simultaneously. What I've done is I've forced all of this whole run method to be synchronized, which means even though I started both threads, only one of them can actually execute the body of its run method at a time. So I have two threads going in parallel, but one of them is blocked by whichever one started first. It iterates 10,000 times, increments the tally, prints out the tally, and then down here we get to the end of the synchronized block. So that's not what you want to do. Okay, you want to keep these blocks as small as possible and ideally only synchronize the thing that can actually be causing a problem, which in this case is just this one increment. Does that make sense? So try-catch blocks, I tell people, you know, put your try-catch block around the smallest set of code possible, and a lot of people don't do that. I'm still seeing try-catches around, you know, 20 lines of code. But it has a definite negative impact if you do that with threads, if you synchronize more than you need to, because you're circumventing the whole idea of threading, which is to have things happen in parallel. Yeah, so synchronized will only pause threads that are also synchronizing on this. If I have another thread trying to do something with, you know, parent.tally and I haven't said synchronize on the same object, it's free to go ahead and do what it wants. And so, you know, you get that good or side, good or bad consequences as a result. And if you synchronize on something that's not shared, right? So I can synchronize on this object called lock, which happens to be a string. But this lock is probably different from the lock in another class. Actually, let's see if this is the case. There's a small possibility. So this is working, and it really shouldn't be, but it is. So here's the thing. So I'm telling you that to make synchronized lock, you have to lock on the same object. The deal is, when I construct a string and I set it equal to ha-ha, it's yeah. So in the JVM, this is why sometimes if you set a string equal to ha-ha, and then you say if string equals ha-ha, it turns out to be true. It's because when it sees quote ha-ha quote, right, there's a string being constructed for that. If I construct the same string in another part of my code or in another thread, it's going to reuse that object. So this is a red herring. that this is actually working. Yeah. Yeah, it is kind of one of those things about Java that worried me a little when I started, which was, you know, it's not a primitive, but you can give it a value by using equal, and you don't always have to say new string, and that feels kind of wrong to me, but we live with it anyway because it's convenient. So I'm doing something now that should be exactly the same, but is doing more what I expected, which was I declared a string, I set it equal to ha, and then I appended ha to it to make it equal to ha ha. Right? But this is not synchronizing correctly because this lock in one thread is different from that same named object in another thread. So these are just things to sort of keep in mind, right? You might think that you can use equal equal to compare things, and if you're comparing, you know, the input from a file to see if it's equal equal quote y, maybe it works, but it shouldn't, right? And the fact that something works is not your proof that your code is correct, right? Your code is correct because you know it's correct. And if you're not sure if something's going to work and you run it and it works, that should make you a little uncomfortable, right? If you're sure that it should work and it doesn't work, that also makes you uncomfortable, but that's a big sign over a gateway which says if you pass through this door, you will become enlightened, right? So that's something you want to dig into. All right, so that's a weird, goofy example, but it was fun that it came up anyway. So we need to lock on the same object, and the easiest way to do that, just have an object that they both share. So you could pass an object to the constructor. We're already passing parent, so parent works perfectly well. But if you didn't pass something in like that already, you could change a constructor to take an argument of some type, and then just lock on that. All right, now there are some times where you may want to lock an entire method. And so let me show you a different way to lock code, to synchronize code. So let's get rid of this. And generally, you know, we don't want to just go in and manipulate a field inside another object. That's kind of a little contrary to the idea of being object oriented. So if I wanted to increment this tally in the Go object, I would call a tally method inside the parent, right? So I tell it who the parent is, I save that here, and then I can just call a tally method, and then you know, here I'm just going to print it out, but I could make a get tally if I wanted. So let me call this increment tally, and let's make this method. Alright, let's see what this does. So we run this and we're back to our same problem before, right? The increments can overlap with each other. Both threads could be calling this method at the same time, and the execution of it can interfere with itself. So we know that we could go ahead and we could put a synchronize keyword here, but it may be once in a while that you actually have a whole method that you want to run exclusively in one thread. And in that case, rather than putting a synchronized keyword in a block around all of the code and finding an object to block on, we can declare a method to be synchronized. So we can just say synchronized. I'm so spelling it wrong. Synchronized public void inc tally, and this method can only be run from one thread at a time. And I did this morning, and it didn't work because I put the increment tally method inside this class. Well, it's a different class, so it's a different method that's trying to execute. But in this case, both threads are going to execute the method inside the same object, which is parent. And so they're both going to try to execute this chunk of code, and since this method is synchronized, it's going to block whoever is trying to run it next, and the thread that runs it first will execute while the other blocks. So we're still just doing a single increment inside here, but this will control things so that we get back to where the final thread is always 20,000. All right, so this brings up the general notion of thread safety. And any time that we have more than one thread running, we've got to kind of be aware of this possibility. And we don't want to just automatically synchronize everything that we do with threads, because then we don't have threading. But we want to be aware that if two or more threads try to access the same object in memory, we can get into these kinds of problems. And so when you look at the Java documentation, you'll often find in the top something along the lines of, this implementation is not synchronized. So this is the linked list documentation, and it's warning you that if two or more threads create a single linked list that they're sharing, you can get into trouble by having each thread just interact with the list randomly. You have to control the interaction to make sure that it's limited to one thread at a time. Now, chances are, if all you're doing is reading from the thread, from the linked list, you might be able to do that with two threads and be okay. But I don't think that's guaranteed. And certainly, if you have a linked list and two threads looking at the same list, and this thread starts moving through and wants to insert a node right here, and while this is happening, this thread decides to delete this node, right? You can see where you might get into trouble, right? Because this thread may have already said, okay, so this new node's going to point here, and this thread may have started deleting this and said, okay, so this thread's going to point here. And now thread 1 will go ahead and it will change this node to point there. And now this node is pointing to a thread that's been deleted, and there's nothing pointing to this node anymore, and your thread is now broken. Your linked list is now broken. But, and I don't know if this is the case or not, but it's possible, for example, that maybe while you are working with a linked list, maybe the structure of that list changes. Maybe as you move through, if it finds that the nodes are stored too far apart in memory, it might compact the list in memory. I don't think this happens in Java linked lists. But it could, right? In which case, you know, if you had two threads reading from the same linked list at the same time, and one of them hit a section of code that caused the list to get moved into a different location in memory, your second thread might suddenly be following a node that doesn't point where it's supposed to. So you have to be careful when you share access to objects. And a lot of what we do in, you know, sort of modern environments involves sharing access. So it's something to definitely keep in mind. And most things that you encounter in the Java documentation will tell you that they're not thread safe or synchronized, so they're thread unsafe. So this raises the question of thread safety in PA5, and we probably don't have to worry too much about it. But let's take a closer look at the threading in PA5. So PA4. You have some kind of on-click listener, which is called when the person clicks the mouse somewhere in the playing field. And so what do we do in PA4 when the person clicks? Well, typically we do something like, we're past some mouse events, so we do x equals e.getx, y equals e.getY, find the row and column corresponding to those xy coordinates, find the closest edge, check the booleans inside that box at that edge to see if that edge has already been claimed. If it has, tell the person that move is illegal. If it hasn't, set the boolean to be true. Set the boolean in the neighboring box if there is a neighboring box. So if we just click the top of this box, click the bottom of the top box above it. Check for a complete box to see if the person finished a box, and if they did, give them their initial. Adjust whose turn it is. If no box was completed, change the turn to be the other player's. If a box was completed, leave the turn the same. So we do all of this stuff when the person clicks the mouse in PA4. All right, in PA5, when the person clicks the mouse, we're going to want to do the same things. Okay, we're also going to want to send this XY information to the other player so that their program can respond in the same way that our program did and show a line and show the initials that are updated and so on and so forth. So that part of PA5 is going to be the same, but we're also in PA5 going to have this separate thread, which I'm calling net thread, which says receive x comma y. And what happens in our net thread when we receive xy coordinates from the other player? We figure out what row and column, find the closest edge, check the boolean, set the booleans, etc., etc. So, a couple of things here, right? First, in PA4, we actually had two different things happening. We could have player 1 click the mouse, or we could have player 2 click the mouse. In your code, you didn't have to make a distinction between those. We had a flag for whose turn it was, but everything we did in the mouse listener was pretty much the same, regardless of who was holding the mouse and pressing the button. All right, in PA5, player 1, player 2 clicking the mouse, totally different ways of getting into our code. When player 1, or when the player who's running the program clicks the mouse, it's going to be a mouse listener event. We're going to do this stuff. But when the other player clicks the mouse, their program is going to send a message through the socket to your program. Your program is going to have a net thread. It's sitting in a scanner call, has next line. When that comes back, it reads next line. It gets an XY message, parses it out, finds the XY coordinates, and now it has to do all the stuff we would have done when you click the mouse. With me so far? So my suggestion is, take all of this and put it inside a separate method and just say, doStuff x comma y. So your mouse listener is a few lines of code now. When somebody clicks the mouse, get the x and y coordinates, call doStuff. And the advantage is in PA5, right, we can say x equals, e.getx, y equals e.getY, and then we can say doStuff x comma y. And then in the net thread, we receive the xy coordinates, and we again just say do stuff, x comma y. So don't write this code twice. Don't write this in your mouse listener and write it again in your net thread, because you don't want to write big chunks of code more than once. Little chunks of code is okay, but big chunks where you have lots of stuff going on and you're developing it, put it in a method. And then the other changes you have to keep in mind is when you click the mouse, make sure it's your turn. So in your mouse listener, first thing you want to do, see if it's your turn, and if it's not, print out a message saying, you know, please wait for the other player to move and return. And don't do any of this other stuff if it's not your turn. If it is your turn, get the XY coordinates, do all of this, and then, you know, net thread, send XY coordinates. Tell the other player about this click that just happened. And then in your net thread, every time you receive a pair of XY coordinates, just call the same doStuff method that, you know, adjusts the booleans in the box and so on and so forth. Does that make sense? So do we need to synchronize this? Technically maybe, but in practice probably not. Even though we have a set of code that can be run from two different places, it's very unlikely to happen. The only way that this do stuff would be executed simultaneously in two threads is if the following happens. It's the other player's turn, I get impatient and click the mouse, and at the exact same moment the other player clicks their mouse, and my net thread gets the message and starts calling do stuff. And I click the mouse right then, and that mouse listener calls do stuff. And chances are, even if that happens, you're probably not going to get into trouble. But there's ways, depending on how you calculate score and so on, or how you calculate whose turn it is, that you might get in trouble. For example, if when it's the other player's turn, you just toggle a Boolean flag, well, if you run net thread twice, it's possible that both of these would toggle and it would end up being your turn again. Things like that. I am not going to test that, and so I don't think it would happen. That would be really evil. but yeah. But you know, you could make this whole method synchronized. It's a short method, and the whole reason this is running in a separate thread is not because we need maximum efficiency and we want this happening at the same time that we're doing other stuff. It's that we don't want to have a call to, you know, while scanner.hasNextLine inside our mouse listener or something else. We don't want to sit here waiting for a network packet to come in. Right, so we're putting it in a separate thread for that. So I would probably just go ahead and synchronize do stuff, make the whole method synchronized, because you get in there, you do a few operations, you get out. Right, so that should be fine. All right, good with that? All right, let's talk about joining a thread. So if you look at the thread class, that didn't work. There we go. If you look at the thread class, right, it has a bunch of methods in here. a lot of these we will not encounter, but join is a useful one. Join basically waits for a thread to exit, and then when it exits, the join method returns. So join waits for a thread to die, and it can throw an exception. So let's use that. So here's the go method, and we construct two threads. We start two threads. Let's go ahead and wait for those threads to exit. And so, you know, right now when I run this, the main thread is exiting really quickly, right? When main exits, the tally is, you know, 600 in that case, 440, right? It's exiting pretty early on. And main is exiting as soon as the constructor for go finishes. And go, you know, creates a pair of threads, starts those threads, makes new threads, calls the run method, and then it's just returning. So main is exiting really quickly. So when I compile this, right, and I say join, it's going to stay here until those two threads exit, and then the constructor will return, and then the main method will print out its exit message. And we should be able to see that main was waiting until the two threads finished. Now if I try to compile this, it's going to complain about an uncaught exception. So we got to put this in a try-catch block. And I'm not going to worry about the exception. I'm just putting that in there to make the compiler happy. So I can compile this, and when I run main, now main is hanging out until both threads finish. And then after the second thread prints out its tally, then the main program says it's exiting, and main is always reporting the correct tally. So you can control your operation relative to other threads, and sometimes that's important. Sometimes you're going to create a bunch of threads that are going to work together to do something, and we don't want to continue until those threads have finished. And rather than, you know, having a flag that gets set, or, you know, checking a tally to see if it's 20,000 or something, we can just call the join method on any of those threads, and that will block until the thread exits, and then join will continue. It'll return and we'll continue from there. Alright, another useful method in the thread class is sleep. So sleep is given a number of milliseconds, and it basically puts the current thread to sleep for that long. And it's a static method, so we don't need a thread to execute sleep. We can say uppercase thread.sleep, put in a time, and it will sleep for that long. And I'm going to make an appeal. Which is, please don't put sleeps inside PA5. Okay, it's a nice way to embellish the user experience, you know, to say, like, you know, game will begin in 3 seconds, 2, 1, go, right? But please don't do that to me when I'm trying to grade, you know, 30 or 40 of these over the weekend. Don't make me wait to play the game. So don't put any sleeps inside PA5, please. But in general, right, we can use this. We can make a thread wait. So let's see. I might already have this. There we go. So here's a class that just counts down from 5 to 0, and after printing out each number, it does a thread.sleep 1000. And we have to put this in a try-catch block because the sleep call can get executed. And so if I compile this and run it, it does a nice countdown with 1 second in between. So that's useful. And you can sleep with a number of milliseconds. You can also sleep with a number of milliseconds and a number of nanoseconds if you want more granularity than a millisecond. So you can go up to 1,000,000 nanoseconds. The other thing to mention in ice cream truck going by where you are, not where I am. I'd go run after it. The other thing to keep in mind is a lot of thread stuff has been deprecated. So when you see something in the documentation that says deprecated, it means it still works, but you're not supposed to use it. It's kept in for backward compatibility, but there's presumably a newer, better way to do the same thing, and so you're not supposed to use these deprecated methods. And there's a lot of deprecation around threads. I don't think a bearded 20-year-old running after an ice cream truck would look good. Hey, you never know. So especially things like stopping threads and pausing threads and so on, these are all deprecated. And there's other ways to do them, but there's a fair amount of confusion around interacting with threads like that. So just be aware of it. And destroy is deprecated, which is too bad because it used to be nice to be able to just like destroy a thread. But there's a whole article you can click through from the documentation and read on why these things are deprecated. And you can always go on Stack Overflow and start a flame war on these topics if you like. And that's a good time. Alright, where are we? 243. Let's get started on something else. So at one time, computers were single-purpose at a time devices. You would take your job and you would load it into the computer and it would execute your job. And then when it was done, you could use that computer to do something else. And after a while, as there were more and more uses for computers became multitasking or time sharing. And so you could have, two different processes both running on the computer at the same time. What a concept. And the operating system would, run this process for a little bit and then run this one and then run this a little more and run this a little more and so on. And so time sharing, right? One of the problems with time sharing, though, is when you have shared resources, you can get into problems a lot less subtle than the ones we're seeing here. So, for example, suppose you have a printer and you have two jobs and they both want to print something. Well, if this job gets a little bit of time, it might print out a few characters of its message, and then when this job starts running, it might print out a few characters of its message, and then this one would continue, and when you look at the printer, you've got messages from two different jobs all jumbled together. So this question of resource sharing and potential resource contention started to be an issue. And so CSE223B, Dijkstra's algorithm, remember that? So Dijkstra explored this using a thought exercise that we call dining philosophers, which I'm pretty sure I spelled wrong. Philosophers, okay. So the dining philosophers, so this is a thought exercise in shared resources, and so we'll start this today, and then we'll talk more about it later. So the setup is you have a bowl with an infinite supply of noodles, and you have 5 philosophers, and they're seated around a table. And these philosophers want to do two things. They want to eat and they want to philosophize. They want to talk. Okay, there are 5 chopsticks, 1 in between each philosopher. And there's a very simple initial rule set. To eat, you need to have a chopstick in each hand. Okay, that's the first rule. So you have to have a chopstick in each hand, and then you can go ahead and you can begin eating. While you're eating, you cannot talk. While you're talking, you cannot eat. And the goal is for each philosopher to be able to eat and talk and not starve and not go without talking and so on and so forth. You are not allowed to cut the chopsticks in half. Otherwise, that's a good solution. You're not allowed to stab the philosopher next to you with a chopstick to take them out of the game. Otherwise, that would be a good solution. So these are civilized philosophers who don't have access to saws. Yeah, good attempt though. All right, so the question is, how do we instruct these philosophers so that they all get to eat, nobody starves, everybody can talk, and so on and so forth? And so you start trying to come up with algorithms, and usually, these philosophers are identical. They're each going to be given the same algorithm, and they have to, by following the sequence of steps, decide when to pick up a chopstick, when to put a chopstick down, and so on and so forth. And so I'll let you think about that, but I'll give you an example of an algorithm. You missed my beautiful chopstick picture. All right, there's the bowl of beautiful noodles. There's the 5 philosophers. Those are the chopsticks. In between them, I'm getting hungry. So here's an example algorithm. Check for stick on the left. If not there, go back and check again. So that's our wait loop, where we're waiting for the stick on the left. Step 2, pick up stick on left. Yeah, we're not going to go FSM here. Check for stick on right. If not there. Did anybody see the Falcon 9 launch today? It went up at like 11:59, which was right at the end of my lab hours, so I was online. If the stick on the right is there, pick up stick on right. Yeah, I said not going to go FSM. Eat for 60 seconds. Put down sticks. Talk for 5 minutes. And then go back up to the top. So there's a sample algorithm, right? But yeah, so an immediate problem with this is, if everybody starts to execute this algorithm at the same time, what's going to happen? Each philosopher will pick up the stick on their left. So this philosopher gets this stick, and that one goes there, that one goes there, and there, and there. And then they all go to step 3, and they say check for the stick on the right, and nobody sees a chopstick available on their right, and so they sit here and they get stuck in this loop forever. So it's possible that this can get us into a situation called deadlock. And deadlock is kind of when you have, 2 or more processes waiting for something to happen, and each one is dependent on something happening in another process, and that other process is dependent on something happening somewhere else. And the only way that this philosopher is ever going to eat is if this philosopher eats, finishes eating, puts down both of their chopsticks, and then this philosopher can pick up the stick on the right. But this philosopher can't eat until this one eats and puts down his chopstick, and so on, and ultimately this philosopher can't eat until this philosopher eats and puts down this chopstick. So it's stuck. And this happens all the time, right? You make threaded code and you run your system and it works great for, a minute, a few days, a few months, and then all of a sudden everything gets locked and it's just frozen and you have no idea why, and it's a good chance that there's some kind of resource contention going on. Yeah. All right, so we'll talk more about this on Friday. We'll play around with this. We'll look at some different versions, but think about this. Do some research on it if you like. It's just a thought exercise, and it helps us understand, how to share resources among multiple processes or threads or philosophers. So we'll play around with that. We'll talk about deadlock, live lock, starvation. I want to take a little bit of a look at this in C also. To just kind of look at it in another language, and that will probably do us for threading, and then we'll go back into some networking stuff. All right, enjoy the day. Have a good afternoon. I will see you tomorrow.